All right. So, let us try and see how we can do this. So, again this is R sub k, this is V sub k, all right, and we have L, we have C. And we are interested in finding what is the noise spectral density at the output. It is 4 kT R sub k mod h sub k of f the whole square is the output noise spectral density corresponding to the kth resistor. And what are we going to do? What do we need to do? Of course, we need to sum over all of them, right, and or you integrate this over. If we are interested in finding the total integrated noise, what are we supposed to do? You integrate this from 0 to infinity and sum over, this is the mean square noise. Is this clear? Okay. So, in other words, the key aspect of the whole problem is, how do we calculate this integral in a simpler way. I mean, one is to say, so go and find all the transfer functions and do this, but you can see that it is a lost cause. So, again we have not really exploited the fact that you have only RLC elements inside the network, okay, and as we did with Nyquist's theorem, we can always exploit reciprocity, but now I will do this in the time domain, right. So, let us say I put an impulse current here. Okay, by the way, before I do that, so this is the frequency domain, and this can be written as 4 kT sigma over all k. I can pull the R sub k out of the integral, right, okay, and you do hk of f the whole square df, that is mean square noise. Does it make sense? Now, let me rewrite this in a form that you hopefully will ring a bell. If I write this as 2 kT times minus infinity to infinity integral mod h whole square df. Is there something, is there some other way of writing this? Pardon? Okay. Right? Parseval's theorem, very good. What is what is that saying? The mean square integral in the frequency domain is the same as the mean square this thing in the time domain. So, this is simply equivalent to saying, well, this is integral 0 to infinity. We know that the impulse response corresponding to hk of f is going to be causal. So, this is Parseval. Correct? Okay. So, now we are reducing to we have reduced the problem to finding this integral, correct, and we still have not used reciprocity. So, since here it seems like in the time domain, it seems reasonable that use the time domain form of reciprocity. So, let us say I put an impulse current here, correct. Okay. As soon as I put an impulse into the network, okay, what will happen? Where is that? If any of this impulse current goes into the network, where is it going to go? It's only going to go into the capacitors, right? It can't go into the inductors because the inductors are going to be an open circuit at 0 plus, right? And the resistors will have an impedance which is much larger than the capacitors. So, all the current goes into the capacitors, right? So, at t equal to 0 plus, let us call, since there is some voltage across some capacitors inside the network at t equal to 0 plus, the network has got some energy, correct? Because these capacitors by hook or by crook have been charged by this impulse current source to some voltages, and as a result the initial at t equal to 0 plus, the energy in the network is non-zero, and let us call that E0, correct? Now, at t equal to infinity, what comment can you make about the capacitors? Well, it is not necessary they be discharged, but there will be some. I will show you examples where it is not necessary that the capacitors be discharged, right? But there will be some redistribution of the impulses come, charged up some capacitors to some voltage and gone, right? Then, the network does its thing and these capacitor voltages redistribute themselves. It is entirely possible, as you guys pointed out, that the capacitors all get discharged, right? But at any rate, at t equal to infinity, there is some energy left in the network. That energy could be 0, right? So, let us call that energy at infinity, let us call that E infinity. Does it make sense? All right. So, what comment can we make about E0 minus E infinity? Remember, power and energy are different things. What comment can we make about E0 minus E infinity? It better be positive, right? Otherwise, we would not be here. Okay, all right. That's one. That's a great piece of insight. What next is do we have? E0 minus E infinity, which is a positive number, right? Which has got dimensions of energy, right? Must all have been dissipated in the resistors, correct? And what comment can we make about the energy dissipated in the resistors? What is the power in the resistor? I square R, right? The energy is simply nothing but the integral of the power. So, it's the E0 minus E infinity is nothing but Rk in the kth resistor is Rk integral 0 to infinity Ik square of t dt. Correct? Is this clear, people? And what is Ik? By reciprocity? Oh, well, what is reciprocity saying? Is saying that the voltage transfer function from Vk to the output is the same as the current transfer function from the output from an impulse injected at the output to the current through this voltage source Vk. So, that is the small h sub k of t. Correct? So, by the way, what are the in all these calculations you have to be very careful about dimensional consistency. Let me ask you a question therefore. What are the physical units of hk of t? Pardon? Okay, let us see how many answers I get. No dimension. The input and output quantity are known. okay, ampere. Pardon? 1 over? Yes, Alfred. 1 over second, that's hertz. Come on, people. Can we decide? Hk of j2 pi f or hk of f is nothing but is the Fourier transform of hk of t e to the minus j2 pi f t dt. All right. So, what are the dimensions of hk of f? It's a gain. So, it is dimensionless, it's unitless. Okay. What are the units of e to the minus x? It's a number, so it's got no units. So, what must be the units of this? This better be what? 1 by time, which is hertz, correct? So, definitely ampere is not correct, it is hertz, alright. So, so when you say if you put delta of t here, you get ik of t, which is hk of t. This is definitely not, this is not correct. Is this correct or no? If I put an impulse there, my claim is that by reciprocity, the current in V sub k must be hk of t. That's dimensionally inconsistent, that's incorrect, right? All you can say is the shape of the waveform is the same as hk of t, but I have to multiply it by what? Hk of t is basically per second, Ik of t is amperes. So, I have to multiply it by ampere second. Where is that ampere second coming from? It is not the charge from the capacitor, it is basically the impulse, correct? Alright, okay. The input current, actually it is the input current multiplied by the delta t in the convolution, right? And so, therefore, it is incorrect to write this as Ik of t as hk. They are related, but they are not the same. One is apples, one is oranges, so you cannot compare both of them, correct? You have to multiply hk of t with ampere second to be able to get Ik. This is subtle, but it's important. Otherwise, you will get results which are dimensionally inconsistent. All right. So, therefore, this is nothing but what is Ik square times what do you call what comment can we make about this guy now? Is this related to hk square of t or not? Yes, no? Yes. So, this is nothing but hk square of t dt, right? This divided by, this times, you have to multiply that hk with ampere second, which is coulomb, correct? So, that is if I divide this by 1 coulomb square, I basically get Rk times integral 0 to infinity hk square of t dt. So, but I needed, and this the summation over k is obvious, correct? Is this clear? So, therefore, what comment can you therefore make about the mean square value of O? VO? Guys, mean square value is nothing but 2 kT times E0 minus E infinity by 1. All right. So, let us start with our typical known case, which is R and C, correct. So, what do? We need to, what is E0 by the way? Let us recall what is E0? The energy you inject an impulse current into the output node and find the energy at 0 plus. So, basically this is R, this is C at 0 plus. What do we see? What happens to the impulse current? It all goes into the capacitor. So, what is the voltage? 1 by C. I mean, hey, dimensions, are we okay? What are the dimensions of 1 by C? I mean, 1 by C is what are the units of 1 by C is? What should it be? It's a voltage, so it must be volts. So, are we sure we are dimensionally consistent? That 1 by C, that 1 is corresponds to 1 coulomb, right, which is contained in that unit impulse. So, when we say 1 by C here, that 1 is 1 coulomb by farad. So, it is indeed voltage, correct. So, E0 therefore is what? One by 2 half times C times V square, which is 1 by C square, which is 1 by 2 C, right, and that 1 is, what are the units of that 1? It is 1 by C, people. What are the units of that? I mean, are we dimensionally consistent? Coulomb square, right? Okay. So, all right. What is E infinity? What happens to this voltage as t tends to infinity? Oh, well, the capacitor completely discharges. So, what is E0 or E infinity? 0, all right. And so, what is the mean square noise? It is, it's well 2 kT times 1 over 2 C minus 0, right. At 1 by Coulomb square and this Coulomb square gets cancelled, right. We remember it's E0 minus E infinity by 1 Coulomb square. Once you do that, there is a Coulomb square in 1 over 2 C. So, that gets cancelled. So, dimensionally we are consistent. So, what is this? This is nothing but kT over C, all right. Now, let us try a less trivial example. So, this is R1, R2, R3, C1, C2, C3, and we are interested in finding the mean square noise across, say, C3. All right. So, as usual, we inject an impulse here. So, where does that impulse current go? At t equal to 0 plus, all the current goes on to C3. So, what is E0 therefore? Or E0 by 1 by E0 by 1 Coulomb square is nothing but 1 over 2 C3. E infinity is well at t equal to 0 plus there is a voltage on C3, right. After a long time what will happen? I mean all the voltage across C3 will discharge through the resistors. What about the voltages across C2 and C1? Well, yeah. So, at t equal to infinity, the steady state voltages across all the capacitors is 0. So, what is the energy at t equal to infinity? 0, alright. Okay. So, what is the mean square noise? It is 2 kT times E0 minus E infinity, which is kT over C. Alright. So, it basically shows that you do not need to, I mean it is wasteful to kind of find the entire spectral density and integrate it and throw away all that information. If you are only interested in the total noise, it is much easier to use some technique like this. Okay. As a final example, let us say this is the output noise we are interested in. So, what is E0? E0 is nothing but 1 by 2 C2. What is E infinity? What is the voltage at t equal to infinity? Pardon? 1 by C1 plus C2, because at t equal to infinity all you need to do is simply replace the resistor with a short, because no current flows through the resistor at t equal to infinity. So, whatever charge there was in C2 must be shared between C1 and C2, and therefore, the voltage at t equal to infinity is 1 over C1 plus C2. So, what is the energy at t equal to infinity? One over 2 times C1 plus C2. Does it make sense, people? Okay. And therefore, the mean square noise is 2 kT times E0 minus E infinity by 1 Coulomb square, and that is 2 kT times kT times 1 over C2 minus 1 over C1 plus C2. Okay. I mean this just is there to illustrate the fact that it is not necessary that all the capacitors discharge to 0. Right. This shows, this is an example of a network where the capacitors do not discharge. Okay. And sanity check, if C1 goes to 0, C1 goes to 0 infinity. So, C1 goes to infinity, it is like having a short circuit there, it should reduce to kT over, alright.